Thank you, Serge. So, good morning, everybody. So, today we are going to talk about the processing of sequencing data, but just before starting talking about it, I would like to have a brief presentation of our team in Rennes, in Brittany. So I'm currently working in a bioinformatics team, and as you know, as you can see, it's about 20 to 25 people, including permanent position, PhD student, postdoc, master student, and so on. And the objective of this team is to develop bioinformatic methods that scale with the growth of genomics data. And our application domains range from health, agronomy, environments, and so on. Just let me explain in the 2 slides what we are doing, and it will, you may understand after that, you may better understand what I will explain during this talk, because the method I will going to present are directly coming from this genomic field. So typically, what we are doing is we are starting from living organisms such as a mouse, soil, and then these living organisms are sequenced just to get the DNA. And then we get generally a high volume of data, and we proceed generally in 2 steps. The first step is to what we call high throughput processing, which directly takes as input the raw data, I mean the sequencing data, and try to organize this data to have more high-level processings corresponding to the needs of the biologist. So typically, the competencies of the team are, as you can see here, data corrections, data compressions, indexing the data, genome assembly, all the stuff you can do when you are working with a biologist. And also, of course, we have a strong cooperation with biologists just to be able to respond to their needs. And now for, I should say, for 5 years, we are interested in DNA storage. So what I'm going to present today is different methods directly coming from the genomic field, what can be used to process data from the DNA storage field. So the focus today is here. So we get reads from the sequencing machines, which are noisy sequences. And then what we want to do is to process this data in order to clean this sequence to input to the final decoding steps. So here is the agenda. I will have a very short introduction to remind you the type of errors we are going to handle. And then also, again, a few words on the sequencing process, just because we are taking this data as input of our process. And then I will continue by presenting the standard methods. We already have heard about it in the last few days. Generally, we cluster the data, and then we make a consensus. And then I will move to new methods called the double graph method, which is an alternative approach to solve the problems. So back to the errors. So as you know now, we have synthesis errors. So Yannick talked about these errors on Mondays. So you know that you can get some oligos of different size, and also there are some missing oligos. On the storage steps, we can also have some errors, such as Marc explains when they talk from the Imagen companies. We can have some broken oligonucleotides. And then the sequencing process introduce errors like substitution, insertion, or deletions. And this is this kind of errors we are going to deal with during this, with this talk. So this is for the errors, but you already know that a little bit. So the sequencing process, as you know, this is, I should say, a random process. Right? When you want to read, you want to get the reading of, for example, 100 sequence, you need to read more data to get this value. So to do that, what we currently do is to sequence several times, and we have the notion of coverage. Typically, in a genomic, when we want to retrieve the data, when we want to use this data, we have a coverage of between 30 to 50. So for each sequence, we will get multiple copies of noisy copies. Okay, so the objective of this talk, of the process, I mean, is to use the redundancy provided by the sequencing data process to provide good quality sequence to input to the decoding stage. So again, the input is noisy sequences in many copies, I mean the reads, and the output, it is a one representative of each sequences with correct size and as few errors as possible. And this is quite an important step, just because it can adjust, I mean, it can have a strong impact on the coding of the data. If we are able to have a good quality corrections, then maybe the power of the code, the inner code we have to put in the sequence will be lower. So this is a trade-off between what we are able to do in these steps and what we are going to put as a code to correct or to check the sequences. Okay, so now let's move to the standard methods. So again, we start from the sequencing data, the reads. And the first idea is to cluster these reads in order to have in a clusters reads which are similar. If you are able to do that, then from one clusters, you can process it to get what we call a consensus sequence. And this sequence is the most probable sequence we can get from the clusters. So this is a two-step process. And what we are going to do right now is to focus on the cluster step. I will say that any clustering algorithms can be used. There are many clustering algorithms which has been designed. And actually, this is not probably not the problem. The problem is probably, you know, when you want to cluster some things, we need to define a distance between the objects you want to cluster. So here, the objects are the reads, And what we want to do is to define a kind of distance between the reads. And there are a few possibilities. I mean, the simple one is to compute a Hamming distance. You know, if you have two sequences of the same size, the Hamming distance is just to count the number of errors between the two sequences. An Hamming distance of 0 means that the two sequences are the same. So this is quite easy to compute, just to detect the errors between the two sequences. But in the real life, actually, we have some of the kind of errors, like the indel errors. So we need to have some more sophisticated distance to compute. And typically, we can compute a Levenshtein distance, which is the minimum number of operations to transform one string into another using the free operations like substitutions, insertion of deletions. So this is a way, you know, to compute a distance between two sequences of different size. So how can we compute this distance? So here you can see this is straightforward. Now, if we move to the Levenshtein distance, it is a little bit complicated. What we need to do is to compute a matrix. So if we want to compute the distance between two sequences, right, we can have one sequence here, one other here, and we have to fill a matrix of size n by n if n is the distance of the length of the two sequences. And one point of the matrix here is the distance between the beginning of the two sequences. I don't know if there is a pointer. Yeah. Yes. You know, a point of the matrix here is the distance between the beginning of this sequence and the beginning of this sequence. And recursively, you can compute the other point of the matrix using this recursive formula. The cost of the indel is 1, and the cost of the substitution is 1. So we fill the matrix, and then we get the distance of the two sequences here. Here, the distance is 3. And a nice way of computing this distance is that we can perform a tracing back procedure to go from the beginning and then to deduce the elements between the two sequences. And this is the optimal, I mean, this is the optimal way of finding a needed distance between two sequences. But this distance here is optimal, but there are different possibilities to obtain this distance. As an example, you know, if you apply the traceback procedures, we have two possibilities of finding this optimal distance. It means that you have a distance, but we have a different way of aligning these two sequences. Now, if we have a look to the complexity of the computation, and what we need to do here, if we have two sequences of length n, the complexity is on n squared. We have n squared computation to perform on this type here. So this is quite heavy. There are some optimizations. Just I give you one flavor or one optimizations. What we want to do here is to find sequence with small distances. And the distance is generally computing the interesting point are on the diagonal of the matrix. So we can just compute these points inside the matrix here, and we can forget all these overpoints. This is a way to decrease the computation. But however, you know, if we want to find all the distances between all the sequences, it can be very, very long. Suppose you have 1 billion of reads. If we want to compute the distance between all these reads, when we have this number of comparisons to do. Even if you have a computer, very, very fast computers, it can take days to compute the distance in that way. So what we are doing usually is to use heuristics to speed up the computations. So I'm going to explain one, just to give you a flavor of what we can do. And it is based on indexing. So what we are going to do here is to take all the reads, the input reads, and to try to organize this data in a way we can speed up the computation. So the indexing is based on a notion of cameras. Cameras is words of k characters. Okay, this is subwords. And what we can do, actually what we are doing, we take the first k-mers, I mean the first word of length k, A, T, G, G, A, C, and we put it in a dictionary. Okay, and together with this word, we put some information, which is the number of the read here, and the position of the cameras in the read. So in computer science, we always start by 0, okay? So this word here, this camera is at position 0 in the read number 1. Then we take the next cameras, the next overlapping cameras. The next one is TGGACC. And again, we put the information corresponding, I mean, in the read number 1, at position number 1, and so on. So for reads of length n, we have n minus k plus 1 entries in the direction in the dictionary corresponding to these reads. Then we take the next reads and we continue to fill the dictionary. As you can see, the next, I mean, the first k-mer in the second read is TGATT. It is here. So the information is read number 2, position 0, and so on. And if we take this k-mer, GATTAG, it is already in the dictionary. So okay, so we had the information of these k-mers here. So these k-mers can be found in the read number 1 at position 8, and it can be found again in the read number 2 at position 1, and also at position 9. Okay, so what you have to understand that all the k-mers coming from all the reads are organized in that way. And we are going to use this organization here to speed up the processing of comparing reads between them. So how can we do that? So it is done using what we call the seed and extend heuristic. So suppose you have a query, I mean a new reads, or reads which can come from the pools of input reads. So let us name it a query. So what we are going to do is to try to find out if there is similarities between this query, this new read, between all the reads which are in the dictionary. So again, you have the index, but also we have all the reads corresponding to the index. So we are doing the same thing. Just take the first keyword, ATTGAC, and just query the dictionary to see if it is in the dictionary. Actually, it is not in the dictionary. So I move to the next one. Again, it is not in the dictionary. Not in the dictionary again. This word is in the dictionary. So when we are faced to this situation, here, the word is in the dictionary. We know that it is in the read number 1 at position 3. So we can map these two cameras together at the right positions. And then this is the seeding process. The facts to have a correspondence between the two cameras in these two reads. And then we can extend using different alignment algorithms just to see if the two reads are similar or not. As you can see here, doing that, we can say that these two reads are quite similar. Okay, so the advantage of doing that, if you do not have to scan all the database, all the reads, you can go directly to the right information. Usually, the lengths of the read here are much higher. We use typically a size of a k equal to 20 or 30. So it means that you can go directly to the right information. So if we want, so we have found one similar read. We can continue the process to see if there are not some other similar reads. So in this situation here, again, we can align these two cameras, but we can see that there is no corresponding, if we perform an extension on the left, on the right side, there is no possibility to find some similarities. Yes, these cameras here are present in different positions, so we can align with the other positions and make an extension on here using the edit distance operations, I mean alignment, the Levenshtein edit distance. We can find that these two reads are similar because there are just one deletion between these two reads. So the seed and extend heuristics does not guarantee to find all the alignment. You know, this is a heuristic. If you have very noisy sequences, if you are using long cameras, then it's possible that similar sequences which are very noisy cannot share the same cameras. So we won't be able to find this similarity between these two reads. But in practice, it works very well, and you get maybe 99% of the elements. So going back to the complexity, instead of computing, if we have 1 billion of reads, what we have to do here is to create a dictionary which is quite linear. So it's a fast process. We have a very efficient method to do that. And then we have, when the dictionary is created, we just have to take the reads, all the reads one by one, and to query the dictionary. And also the complexity is quite small. You know, for one read, instead of computing the similarity between all the reads, we just compute the similarity with a very small subset of the input data. So this is a very fast process. So, yes?
How do you decide the K value, the size of the kernel?
It depends of the applications. You know, if you have a very huge volume of data, you have to choose a k-mers of length quite long, just to be more specific. If you are, for example, working on a small set of data, such as bacteria, then you can narrow, you can decrease the size of the k-mers. But generally, this is a user parameters. So it can be set on the different programs, and this is the experience of the users to say to. I mean, this is the responsibilities of the user to set the size of the k-mers. If we increase the size of the k-mers, the time of the computation will decrease. Just because if you increase the size, you know, the number of possibilities to find long k-mers into overreads will decrease. Actually, so it may be a little bit longer to create the dictionary, but not too much. But if you, for example, if you increase the size of the k-mers of one positions, then you will have 4 times less possibility, and then you will decrease by 4 the execution time. So, but you're right, there is a direct correspondence between the size of the k-mers and the time of the computation. Yeah. Okay. So now we have a way to compute rapidly the distance between the objects. Here the objects are the reads. Then, as I was saying before, we can use all the panels of clustering algorithms we have. I won't describe this panel. I think you will have the slides, so you will be able to choose the algorithm which best fit with your applications. In the context of DNA storage, what we want to do is to make some clusterings, and we may know the number of clusters we want. So there is an important parameter here, depending on the class of clustering algorithm you choose. If you know the number of clusters, then you can select some algorithm which will be more appropriated for the use. Just an example of what we can do or what we are doing generally. You can use a graph clustering. In the graph here, each node is a read, okay? And there is an edge between 2 nodes. Is the distance between the reads are under, for example, a given threshold. Example, okay. So you get this kind of graph, and then you can apply some algorithms such as to find out the connected component of the graph, which will give you the partitioning. And then you can, for example, as you can see here, group, extract the cluster of the graphs. Okay. But there are many algorithms to do that. So again, I won't describe this algorithm today. It can be a little bit more complex than connected components. As you can see here, you have a connected components, but we can split it again to find pseudo-click or something like that. But again, in computer science, there are many ways to cluster these kind of things. And I have no time today to describe the process. Okay, so we have seen the clustering process. Now we are going to move to the consensus, which is actually, from my point of view, a simpler analysis. So a consensus, what it is, you get some similar sequence, which are the reads here, and then what you want to do is to find a sequence here which comes from this set of noisy sequence. So we have to use some consensus algorithm, and it's usually performed by applying to this set of sequences here what we call multiple alignment algorithms, and this kind of algorithms give you a multiple alignment here. And when you have these multiple alignments, when you can just vote, you can just perform a majority vote to get the sequence. Okay, so again, there's multiple ways of doing this multiple alignments process. We can use the dynamic programming I've shown just a few slides before. It can be used for 2 sequences, for 3 sequences, for 4 sequences, but the complexity is depending on the number of sequences. But again, there are some heuristics to perform this kind of process. Here is a short overview of the literature on this multiple algorithms. And, but you know, here this is not very difficult, just because the number of sequences here is generally low. You have a few sequences, a maximum 10 to 20 sequences, and it's a very fast process. And when you have done the clustering, you can parallelize this step on modern processors. So from my point of view, this is not the bottleneck of the processing. The bottleneck is rather the clustering process. So I would like to introduce another way of computing a consensus, and it will be the opportunity for me to introduce also the concept of debranch graphs. We will use later on this talk. So we start from the list of reads. We decompose these reads into camers. So you know now what is a camers. Then with this set of camers, we are building a graph. I will explain it in a few seconds how this graph is built, but it's a specific graph called the debranch graph. And from this graph, we can navigate into this graph and to extract directly the consensus sequence. So let us explain step by step how it works. So the first step is to extract camers. So I take the first reads, the first sequence, and from this sequence, I extract all the possible camers. So this is all the camers in blue here, okay? I do the same for the reads, the green reads, sorry. So we have new camers, but also we have some camers which are shared by the 2 sequences, okay? I continue the process. Again, we have new camers, and camers we are shared by 2 or 3 sequences, okay? And I continue. At the end, I have the list of all the cameras which are present in the reads here. But as you can see, there are some cameras which have only one occurrence. Okay. And the nice thing here is that these cameras, as you can see here, are more or less in the part where there are some error here. So just to give you an idea of this toy example, I've made the alignment here, but in the reality, you have longer sequence, and this step is not done, is not performed. So the hypothesis, the assumption is that cameras which are in single occurrence, cameras which are seen only one time, probably are cameras inside sequence which have errors, okay? And the useful information is the cameras which are present several times in the data set, okay? So after the first step, we remove all the cameras which are seen only one time, okay? On this toy example, generally, if you have much more sequence here, for example, I don't know, 1,000 sequence, then we can also remove only the cameras with one or two occurrences. But what we keep is only the cameras which are seen many times. So we called these cameras solid cameras. And we are going to use it to build a graph, which is called a doubling graph. The nodes of the graph are the cameras. And we make a link between two nodes if the prefix of one node is equal to the, if the suffix, of one node is equal to the prefix of another one on k-1 characters. So the nodes are cameras, and we make a link if we have these conditions. So the next step, after removing the wrong cameras, is to construct this graph using the rule I've just explained. I mean, the suffix of this camera is equal to the prefix of this one. Okay. So when we have done that, we can use some information we can have on the read. For example, if we know that the reads are beginning with a primers and ending by another primer, so you have some information on the reads. So you can use this information to navigate the graph. So you can start from a k-mers extracted from the primers, and then navigate to the graph. And then, as we see solid cameras here, I mean cameras with a lot of information, with no noise, then it's possible to retrieve a path corresponding to a consensus sequence. Yes?
Does this use the fact that you know the length of the reference sequence or not?
Yes. Here, if we know the length of the reference sequence, it can help to improve the navigation in the graph. But you're right, the idea is that we know the first chimer, we know the last chimer, and also we know the length of the sequence. All the sequence which can be found with another length can be discarded. Okay, so it was just to explain you another way to find a consensus starting from a cluster of sequences. Okay. And this will help for the second part of the talk, where I'm going to explain how we can remove or how we can merge the clustering on consensus step into one single step, working from using a double-branch graph. So here's the method. Is to merge the clustering on consensus steps using a global double-branch graph. And this graph will be elaborated from all the input reads. And again, this is possible because we are in the case of DNA storage, and we have some information on the reads. Especially, we know generally what are the start primer and the end primers. We know the length, we know the payload, we know where are the checksums, etc. We know a lot of information we do not know in the genomic field. So we are going to use these informations to help to improve the clustering and consensus step. So the idea here, the global idea, is that all the reads coming from the sequencings will be processed together, no clusterings, and we are going to use all these reads to construct a double-branch graph directly. I mean, there is no further processing on these reads. There will be split into cameras. Okay, we will build a huge graph, and we will use this graph to extract directly consensus sequences. So I'm going to explain step by step how we are going to do that, but this is the general idea. And I mean, the idea is the following one. In the set of reads, of course, you have some reads which are similar, and there will more or less will be some kind of subgraph in the graph here from the start to the end. Okay, so for example, these three reads here, which are similar, probably they will all communicate with similar cameras in the graph here. And then the idea is to enumerate all the possibilities of the path, starting from a node we know, a camera we know, which belongs to the primer, for example, the starting primers. So what we are going is to enumerate all the given path from this point to this point. And this will give us some candidate as consensus sequence. But because remember that all the nodes of the graphs are solid cameras. I mean, very useful information. Okay? All the cameras which have been seen only one time have been removed. So this is a very interesting information. The information is supported by these cameras. So when this graph is built, it can take some time, but we have some very efficient methods to build this graph. You can navigate on it from this point to this point and enumerate all the possible paths. On this path are possible candidates for consensus sequences. And actually, it works very well, pretty well. There is just a question of scalability. If you have in input this number of reads, a few billions of reads, then the graph here will be very, very huge, okay? And the graph will be complex. And when we are going to navigate to the graph, we can have some cycle in the graph, which are very bad for enumerating all the possibility. And the extraction is becoming very complex, long, difficult, and you can have many false positives. So what I explained to you works well on small set of data, but we have made some experiment. It doesn't scale for a huge amount of data. So how can we proceed for using this method? How can we break the complexity? So the idea here is not to make a clustering, but is to make a partitioning of the data. So the idea is that we have this set of data here, a lot of reads. Then we can split this data into some subset of data which are much smaller. And from this smaller set here, we can we can build a double graph and then extract the consensus sequence. Okay, so this is the main idea. But this scheme is working only if we are sure that the copy of the same oligos are in the same files, of course. Okay. If a copy of oligo is split over all these files, then the method won't work. So the trick here is to find out a partitioning which put into these files all the copies of the same oligos. So how can we proceed to do that? So a very simple strategy, again, because we know we have some information on the reads, especially the primers. We know that after the primers, this is the payload, or this is the index, or this is something else. But we can use this information here to perform a partitioning, knowing that the same noisy copy will probably have the same first nucleotide here. So we use this information, which are specific for each oligos, to perform the partitioning. For example, if we take the 3 first nucleotides, then it's possible to partition into 64 subset. And we can get subset, and if the size of the subset are still too much high, we can recursively split it again. So as you can see, but you know what you have to see is that performing this partitioning on this first information here ensure that the same copies of an oligos will be in the same subset. This is the trick here. The advantage is that this is a very, very fast process. The computation here is nothing. We can fully control the size of the Dobrinj graph. The size is directly proportional to the number of reads for constructing the graph. And when we have done these partitionings, we can proceed all these operations in parallel on modern computers. Okay, so we have implemented this software and this method in a software which is called Conclude, and it has just been published last Sunday. And of course, we wanted to make some kind of we have made some experimentation on it just to see if it scales well and if it gives good results. So we start with, so we make the experiment of synthetic data. So this is the data we generate. So on here, 30K oligos with 500 reads. So it takes a few seconds to perform the computation. Then we take 10 times larger data, then 100 times larger data. And what we can see is it scales perfectly, and the scaling is proportional to the number of reads we have to process. And from the precision on the recalls, this is the blue and the green bar here. You can see that from a precision point of view, we get 100% precision. And the recall depends of probably, it's not 100%, but it just depends of the reads which are present or not in the data set. All the reads have been simulated using some simulators we can have now. And we also perform some experimentation on real data. And on real data, it gives us also the same performances. So this is a very, this is a very efficient method to generate consensus, which can be used as input as a decoding step. And it's also a very fast method. So, as a conclusion, of course, we need to process reads before the decoding stage, but all the reads won't be corrected. So we still need some inner code to correct the remaining errors. What we use here is a redundancy of sequences to correct as much as possible errors. And as I was saying at the beginning, there is a trade-off between the power of this method and the power of the code to include in during the coding step. If we are able to correct all the reads, probably what we have to include as redundancy in the inner code can be quite small. And then there is a trade-off between the coverage and the synthesis. It depends on the cost of both. But what it is interesting here is that what I have presented using, the Dobrinj graph method comes directly from the genomic field. And on the DNA storage field, I think, how can I say that the problem is much more simpler. In genomic, when you are sequencing some unknown organisms, we know nothing about it. You know, we do not know the length of the sequence. We know that they can have a large homopolymers and so on. Here, we are on a constraint situations. We know the length of the reads. We know where are the primers. We have some possibility to perform some checksum and so on, some corrections. And all these informations can be used to adapt the genomic method to the DNA storage method. And to, as you can see, to have a very efficient method, not based on the classic idea, but coming from the genomic field. Okay, so this is the end of my talk. If you have any questions.